7. And what does question 7 say? It's 1.3, right? Supposed to draw a graph and satisfy it. What did it say? So it just actually draw a graph?
Yeah. Sketch a graph. Yeah.
Okay, what are the restrictions? They're from the left should be. Okay.
And then from the right, it's positive.
F of what?
X.
F of 0. F of 0.
F of 0.
F of 0 equals?
That's it.
That was it.
Show a graph that satisfies those
conditions, yeah.
We did a graph that satisfies both of them, sorry.
Actually, the limit from the right is supposed to be 2.
Yeah.
I got 2. Yeah.
Are you guys asking me from WebAssign or is this from the book? Well, I mean, any other questions? Yeah? You could have done like anything, right? You could have been like, you could have been like, It doesn't really matter. Yeah. As long as when you're coming from the right, you're getting close to y value 2, when you're coming from the left, you're getting close to y value -1. And
So why do you make it like this?
you're,
Why do you make it like an R?
what do you mean?
Like this, R.
Well, that wouldn't be a function, right? Because it wouldn't pass a vertical line. Right, but anything that you can draw that's a function, that's like,
But this one doesn't say it has to be a function.
yeah, it's like a function, right? I mean, we're assuming that we're
Oh yeah, it says graph and example.
yeah.
So if it was not a function, then we could have.
Yeah, you could have done anything. You could have been like, but we need a function, so it has to pass a vertical line. That's where we're Other questions?
Do we have quiz tomorrow?
Huh?
Quiz tomorrow?
Yes, there's a quiz tomorrow.
On just
The
section
quiz will be on everything I cover up to today, and between the last quiz and what I covered up to today. In general, quizzes are not cumulative. The tests aren't cumulative either. The other questions? Yeah.
If you finish 1.4 today, I'll be on the quiz tomorrow.
Yes. Anything I finish today is on quiz.
Let's try not to finish something.
No, I'm pretty sure we'll finish 1.4. I did a bunch of these examples. I don't remember what they did. Okay, I think that's the big You guys can pass the homework up to the by the end of the semester. Alright, so we're going to talk about the direct substitution problem. Hey guys, quiet down. Be quiet. We sort of applied this before, but basically said that there are certain types of function where you you can just plug in the number to find the limit. Right, so if f is a polynomial, rational, or Trig function, and a is in the domain of f, then the limit as x approaches a of x is simply just f of a. You can literally just plug the number into the function, whatever answer you get, that will be the limit. This actually works in general for continuous functions. We'll cover that in fact, it's the definition of a continuous function. But we'll leave our discussion for continuous functions for section 1.5. So basically, you have a polynomial, a rational function, or a trig function, then if you're taking the limit as x approaches a, and a is actually in the domain, you just plug it in. You don't waste your time trying to move stuff around. Alright, so we actually did a few examples of this, so limit as whatever. You can literally just plug it in. 2 squared plus 2 times 2. So as long as it's in the domain, you just plug it in, right? It doesn't always work, of course, right? Sometimes plugging in is really bad. Like when a is not in the domain for obvious reasons. So for example, we also looked at things like this before, but I just want to state it formally. X approaches 2 of 2x squared minus 8 over x minus 2. In this case, plugging in is actually a bad idea because in the denominator, if I plug in x equals 2, I divide by 0, which is illegal. How would you actually do this one? Factor. So you try to see if there's some way you can get rid of that pesky x minus 2 in the bottom. Now what's that?
You find the x minus 2x plus 2.
X minus 2x plus 2, that's the difference of 2 squares.
Cancel out the x.
Then you cancel the problem.
8.
And now it looks like a polynomial where 2 is in the domain. You can literally just plug in the 2. 2 times 2 equals. So this limit is 8. Notice that at 2, the function is not defined because you actually divide by 0. In fact, here, if you were to graph a picture of this function, it would look something like this. Go to 4, 2, and when x is 2, there will be a hole. It will be around the level of 8. Right? So don't let the limit trick you that you can actually plug in 2, divide by 0, the answer is 8. That's not what's happening. At 2, it just doesn't work. But the limit works because it doesn't care about being at the point, just getting super close to the point. So as long as x is not actually equal to 2, the thing is going to behave like it's going towards 8. So it's a very important distinction. We'll keep coming back. Actually, gave me that example already. some more examples for you guys to work on. Okay, so if I actually wanted to find this limit, how would I actually do it?
You square the 2 plus 8.
Sure. Plug this into the x minus 2 into the x over h, and then
You get 4 plus 4h plus h squared minus 4 over h. And now you get over 4h plus h
so it's
squared.
cancel.
H plus cancel.
I can factor out an h,
4 plus h. 4 plus h.
which cancels the bottom, right?
Yeah. So
And
that's
so now I can actually let h approach 0, and the answer will be 4. Now, this number actually means something. When we get to chapter 2, you'll see what it actually means. But yeah, that's how you do the limit. Just some things about notation. Notice that I keep writing the limit thing until I get to a point where I can actually take it. Then I don't write it anymore.
Professor, what if you write again at the result? Would it be incorrect?
What do you mean, like right limit here?
Yeah, the limit of s h
Yeah.
versus 0
No.
equals 4.
I mean, if you write this here, it's just equal to 4 as well.
Okay, would that be correct? If you write it?
Technically, no, but I would probably cut the point. Just a coincidence. It's not incorrect because this is a constant. If it was anything else, then what do you do? How about this one?
Is multiplied by
Radical 1 plus 2x plus 1.
Plus 1, right? Because that rationalizing trick again.
so you get x times 1 plus 3x plus 1 minus 1 minus 1.
Right? So now the 1's disappear, and because this is multiplication, I can actually cancel the x's as well.
1 plus 3x plus 1.
That's just radical of 1 plus 3x plus 1 all over 3. And now I can just plug in x equals 0. I get 2/3. Notice that in the beginning I could not plug in x equals 0 because if that's 0 I'd get 1 minus 1, which is 0. That's bad. You couldn't do direct substitution. So you try to simplify it. And sometimes you can actually cancel the problem. What?
It turns into 2 after the radical and then 2 plus 1 is 3.
No, x is going to 0. So this is gone. It's just radical 1 plus 1. Here is just a general theorem for you to know. Suppose you have a function that's always less than another function. X equals a, and the limit of x approaches a of x, and limit of x approaches a of g of x exists. Then limit f of x is less than or equal to limit of g of x. Limits actually obey inequalities. Right? This will always be true. Another very important theorem that sort of depends on this is called the Squeeze Theorem. Or sometimes you might hear it called sandwich theorem. And it basically says the following. Suppose you have f of x, h of x less than or equal to f of x, less than or equal to g of x. A, and further suppose that the limit as x approaches a, h equals L, and the limit as x approaches a of g also equals L, then limit as x approaches a of f of x must be equal to L as well. They will have no choice in the matter. Well, just to give you an idea of why this works, because limits actually obey inequalities, this means that the limit of the h must be less than or equal to the limit of the f must be less than or equal to the limit of the g. But we know that this is L, and we know that this is L, right? So limit of f is both greater than or equal to L, and the limit of f is also less than or equal to L. Well, the only possible way for that to happen is if it's actually L itself. This is called the squeeze theorem. And it shows that if you can actually squeeze a limit between the same number, the limit has to be equal to that number. And there are cases where that sort of trick helps us solve problems. For example, thought about this one. Do you have questions on that? So there are a lot of limits that the squeeze theorem can actually help you with. This case in point is one of them. Notice that we cannot plug in x equals 1 because we divide by 0 inside it for the angle of the cosine. But at the same time, we can't really simplify to get rid of it. Right? You can't cancel into the angle by something that's outside. So we can't get rid of this x minus 1, so what, does it not exist? Actually, it does, right? So how we know that it does is, first we know if x is actually not equal to 1, then we have the following. Cosine of 1 over x minus 1, we can actually bound it between two things, right? What is cosine bounded between? Negative 1 and 1. Cosine and sine are always between negative 1 and 1. This tells you two things. This means that if I look at this guy, x minus 1 cubed times cosine of x minus 1, then this has to be less than or equal to x minus 1 cubed times 1, and it has to be greater than or equal to x minus 1 cubed times minus 1. That has to be true because the smallest possible value of cosine can be is negative 1, so the smallest possible value that overall can be is negative 1 times this.
It says it's not equal to 1, right?
Yes, when it's not equal to 1. Because I can't be equal to 1. Divide by 0.
In that domain, it is less than or equal to, doesn't 1 exist?
Come again?
In minus 1, less than or equal to cos 1 by x minus 1, greater than or equal to 1.
Yes, x cannot be 1 because of this, not because of the cosine. The angle is where the problem is. I can't plug in x equals 1. But I can get as close to 1 as I want, and for any value not actually 1, this will hold true. Cosine will always be between minus 1.
If you put like that greater than or equal to sign, isn't that 1 fall into the domain?
What do you mean greater than or equal to sign?
Isn't that you just put the greater than sign now?
This greater than?
Yeah, I mean the other one. Greater than sign. This
Not
one.
sure. This?
Yeah.
What about?
Are you using equal to, right? So you're using equal to.
Yes, maybe less than or equal.
So doesn't that include 1 in the
No, these are the range values.
The whole thing, no? You're saying just x minus 1 is not it can't be 1.
The maximum y value is 1, the minimum y value is minus 1. Right? The function is going to bounce up and down there. Right? But when you get to x equals 1, you're like a void, you can't touch it. But other than that, it'll just keep doing what cosine does.
Okay.
Right? So its maximum value is positive 1, minimum value is negative 1. Which means that this inequality actually holds. Which means I can take the limit of this inequality. Limit as x approaches 0 minus x minus 1 cubed must be less than or equal to the limit as x approaches, 1. X approaches 1 of x minus 1 cubed times cosine of 1 over x minus 1, which also must be less than or equal to the limit as x approaches 1 of positive x minus 1 cubed. Right? I can just take the limit across the inequality, because limits obey inequality by this theorem. Well, what is the answer here? Zero. That's actually continuous. You can just plug in the number, right? You plug in 1. This will go to 0. And what would this one go to?
0.
Also goes to 0. So what do you notice? This limit is between 0 and 0. It has to be 0. How are you going to be between the number and itself? So this is actually a very common trick. You know about sine and cosine and what bounds them because you did that whole pre-calc review and you know everything about sine and cosine. Right? So you can actually bound this, you can throw in an inequality because this guy works, the squeeze theorem works when you have that sort of inequality. Right? So if you look at something and you can't really simplify it and you're trying to think what else to do, this is one thing you can try to do, especially if you can bound one of the functions. Right? So because I realize the cosine part is between -1 and 1, then overall the expression must be between this and that, right? And it just so happens that both ends go to 0. So this limit, if it exists, whatever the answer is, it has to be between 0 and 0, and in order for that to happen, it has to actually be 0. So this limit is actually equal to 0, and we use the squeeze theorem to determine this. Because algebraically canceling stuff just didn't work. So it's just another trick you can use sometimes. This is a very typical example, like most textbooks that introduce this would probably go with this example first. This is a very famous thing. The graph for this actually looks like you just have to be constant. It's a very famous example, but as you go to 0, it doesn't exist. There's a hole here at 0 because of the 1 over x. However, the limit does approach something, and you can sort of see from the picture it's going to approach 0, but how would you actually prove that? The answer is you prove it using the squeeze theorem.
It's only used for sine and cosine and tangent?
No, it's like the typical example. Like you couldn't use it for tangent. Tangent goes from infinity to negative infinity. Tangent has an infinite range. It wouldn't really help you much for tangent. But yeah, so again here, you know, as long as this angle is a real number that we can actually plug into sine, it will only give us outputs between these two values. This means that minus x squared is less than or equal to x squared sine omega x, which is less than or equal to x squared. Which also means again, this goes to 0. That goes to 0. So this is just a trick that says sometimes when you're given a limit, if you can find something bigger than it and smaller than it, where their limits go to the same number, you can force this limit to be that number. And you can figure out the answer that way. And typically it will be sines and cosines or trig functions where you know their bounds. Right? For example, tangent inverse shows up a lot of times too, because tangent inverse is bounded between power 2 and minus power 2. So anything that there are functions where you should know what their boundaries are, and they might actually throw those in problems where you should be able to say, oh, well, this has to be this big or this small, and then you just sort of squeeze it. This is called applying the squeeze theorem.
Does that always happen? That's equal to 0 in the end?
No?
No?
It would be easy to come with something that doesn't go to 0. I could do something like the limit as x approaches 2 of x plus 1 squared the sine of 1 over x minus 2. What give us the same answer? Something like this. So in that case, this guy this is going to be between the limit of the absolute value of x plus 1 as x approaches 2 and I want somewhere where the negative sign won't matter. It doesn't have to be 0, but I can't think of an example off the top of my head right now. I'm pretty sure on your homework you might see problems. Yeah?
Can't you just have approach a negative number and use an odd exponent outside of the
An odd exponent?
Yeah, with no negative.
You mean for like
negative 3, x plus 1 parentheses, the exponent of 3.
No, because you'd still get, this guy will give you the negative on the outside.
Oh, yeah.
Right, so this is not the problem, it's the sign that's the problem.
Yeah.
Just give him the negative outside of whatever you do. Sort of strange. It is possible to not get 0 at this. You can't think of an example off the top of my head right now. But yeah, this is actually a very common trick, especially when you see trig functions like squeeze them. You use these sort of relationships all the time. Sine is between minus 1 and 1. Or if it's actually a square, you know, it's between 0 and 1. Right? These kind of relationships you will use all the time. Speaking of trig, there are things that we call the special trig limits. This is a very famous one, you should know that. It also means that the limit as x approaches 0 of x over sine x equals 1. Moreover, you know that the limit as x approaches 0 of tan x over x equals 1 is a very important equation. Because it equals 1, you can actually flip it as an inverse. So x approaches 0 of x over tan x is also 1. Also the limit as x approaches 0 of 1 minus cosine x over x is actually equal to 0. Of course, for x not equal to 0. Let's talk this our pre-box formulas above have a name. They're called the special trig limits. So if I ever say I apply the special trig limits, these are the rules I'm talking about. I mean, I apply one of these rules. Let's actually do an example involving these guys. So if you're interested, you can read the proof for this in the book. It's not that bad. Don't want to go over it. But these three limits, you should know their values, you should have them memorized. They're very famous, they're very special, and they show up all the time. Here are some not so complicated examples where they might show up. So what's the limit of this one? I think the limit is 5. Why would you say it's 5?
Sine x over x is 1 and 1 times sine x.
Yeah, but you don't have sine x over x. You have sine of 5x. How did you get that?
Yeah, first you get rid of the 5.
How do you get rid of the 5?
Multiplying by 5.
Can you distribute it to the
5 is already 5.
Oh, you cannot factor things out of the angle.
You multiply sine of 5x over x by 5 over 5.
Sure. You can multiply this by 5 over 5. Now with multiplication, I can start to shift things around once they stay at the same level. Which means this 5 here, I can multiply the x there. So this would be sine of 5x over 5x times 5, right? it's very important that you realize that the angle and the denominator have to be the same thing, right? So if it's not the same thing, you have to sort of create it some artificially, right? So here the angle was 5x, the denominator was only x. That wasn't good enough to apply this rule. The angle and the denominator have to be the same, and they both have to approach 0. So it wasn't the same, we made it the same, right? You can multiply by 5 over 5, there's no problem with that. And so now, by the special trig limits, this will actually go to 1. And so the limit overall is just 1 times 5. It's actually 5. Okay. What about a problem like this one?
6 over 5.
You think it's going to be 6 over 5? Okay, tell me how.
Because you multiply everything by 6 over 5.
You want me to just multiply everything by 6 over 5? How's that? 5, 6.
Okay, that's not
We just go randoms.
Yeah, you can just turn around. What do you mean do both?
Like multiply by 5 over 6 and 6 over 5.
Okay, does that help?
Then you
Write down the square of 1 then.
Right, you want to apply this rule, right? You want to get tangent of some angle over the angle itself, or the angle over tangent of the angle. So what are the angles? You have 6 x's and 5 x's, right?
What if we convert that into sine and cosine?
That's, I might get it a mess.
You could, but you don't have to.
Would that make
The angles are 6x and 5x, so what do you think we should start with?
First, multiply everything by 5x.
Notice that this is the same as tangent of 6x over 1 times 1 over tangent of 5x, right?
Yeah.
So if I want the top to be what? 5x. So what do? Multiply by 5x and divide by 5x. Here I want the bottom to be 6x, right? So I'll just multiply the top by 6x and the bottom by 6x. Now in this case I can move the denominator over here because it's multiplication. And in this case I can move the numerator over here. It's multiplication. Right? So now I will have 6x times tangent of 6x over 6x times 5x times tangent of 5x over tangent of 5x times 1 over 5x. And now what happens? These guys I know will go to 1. Right? Here the x's and the x will cancel. So the answer is 6 over 5. And these problems are typical and they can get even nastier, but the moral of the story is they're never just going to give you something that looks exactly like that. They're going to give you something where you have to like do some sort of manipulation, multiply and divide by the same thing, try to move things around. Or they're going to try to see if they can trick you into missing it. Any questions on this? Yes.
So the special trig limits.
Are those three?
Okay.
Limit as x equals 0, sin x over x equals 1, tan x over x equals 1.
Are they the forms or are they the trig functions? So like cosine can only be written in that form, tan can only be written in that word. What do you mean?
Well, you have some leeway with it. X. Right? Your x can be any formula in here that approaches 0.
Now, does that mean like sine of x over x is the same thing as tan x over x, but you change the sign of tangent? So can you have cosine x over x?
Oh, no.
Oh,
It
so
won't
that's what
work.
I meant. Okay.
Right. Yeah, the sine, where you see sine and cosine, it has to be those functions. Right. The only thing that might be different is the angles. But as long as you can realize that they're going to 0, you can apply them like a general formula. But yeah, you can't do that cosine to sine here. It won't work. I'll just count. Yeah, this one cannot be flipped because it equals to 0. Flipping that side would be equivalent to flipping this side, which would be equivalent to divided by 0. That was actually equal to 1, so yeah, you can flip 1. So those two you can flip. This one can't be flipped. And these can... I mean, there should be a lot of more implicit examples like this in the homework as well. But that actually covers 1.4.
Wait, what did the example of cosine? What?
The example of that one? What?
Before we leave 1.4, we're doing example now.
Limit x equals 0 of 1 up. That looks semi-interesting. Let's see. It's one that's sort of interesting. How about that? What do you think the answer is? How do you prove it? So your first instinct might be, oh, you see the sign and the x on the bottom, let's split it up. The problem that doesn't work because it's an x squared. Right, so that's sort of, you're getting in trouble there. And you can't just run and go, oh, just square the sign so it works. You can't do that either. So what's the trick here? Yeah.
I think you have to realize that sine 2x is a double angle formula. So you rewrite that as 2 sine x cosine x.
So this is actually sine x minus a half times 2 sine x cosine x. Okay, then what?
cancel the 2's,
2's can cancel.
and then you factor out a sine x.
You factor out a sine x.
And now you can split the x's up. You can split the x's up now.
Right, I can actually take this x squared and put one of the x's under here.
And you just use a special trig limits now.
Now you use special trig limits. This guy goes to 1, that guy goes to 0.
Yeah. Cool. Cool.
The x becomes 0.
What?
Like sin of 2x equals 2 sin x cosine x, right? Like, you know those things like that?
Well, that's why we did the trig review, right?
No, it's not.
Yes, it was. It was on the diagnostic at least. What's cosine of 2x?
Cosine squared x minus sine squared x.
See, how does he know? Because he did the review. Give me another form.
Oh, that's probably what I
1 minus.
Just do like cosine squared.
Cosine.
Yeah, if you change cosine squared to 1 minus sine squared, you can write it like this. Or if you change this to 1 minus cosine squared, you can write it like that.
We are not
Right.
memorize this, they give it to us in formulas.
Oh, I didn't know.
That's part of No. No.
Don't laugh.
In high school, baby.
Yeah.
No, we expect you to have this all in your head. This and a lot more other ones. Yeah. There's no formula sheet. Those days are gone. So gone. Yeah.
How much longer are we going to be in a topic where it's heavily trig-based than algebra based before we get into the hardcore calculus?
I don't know. We're sort of going to be doing trig the whole time. Like in every chapter where I do an example, there will be trig examples also. Yeah. But trig actually comes back with a vengeance in Calc 2. So if you suck at trig, Calc 2 will be not trig. So I'll just start with the main definition, 1.5. We won't really do anything. I just want to talk about the main definition here. 1.5 is where we talk about continuity. All right, and the definition is the following. Function f of x is said to be continuous at a point x equals a if the limit as x approaches a of f of x is actually equal to f of a. That's that. We've seen this before. It is continuous on an interval if, what was the equation 1? If 1 is true for all points in the interval. F of x is called continuous. Like continuous in general, right? There's a difference between being continuous at a point and being continuous in general, right? F of x is called continuous in general if 1 is true for all points in its domain. But I sort of wanted to talk about this definition and sort of what it means. It's one of, like equation 1, it's one of those equations in math that where you really see how math can take this intuitive concept and just describe it in a single equation, very short, concise, neat equation, right? Because if you were to, just by what you know about continuity, if you were to describe in words, like what does it mean for a function to be continuous, and you wanted to describe this to someone, what would you say? Right? What does it mean to be continuous? What does it mean to be continuous? Gary, explain this. Huh? This keeps going, there's no break, no distortion, no gap, no jump. If you're drawing it, you can do it without lifting your pencil off a page, right? All of that is captured in this equation. If you don't believe me, let me show you, right? What does continuous mean at the point A, right? It means I can draw the function through the point A without lifting my pencil off the page, right? This is called f of A. Right? So what would you notice here? Well, limit as you're approaching the left is f of A. Limit as you're approaching the right is f of A, right? The function is defined and is equal to f of A. Right? So you say, okay, great, works for continuous functions, but how do you know when something is not continuous? Well, this is if f continues at A. Let's look at if f is not continuous at A. What are the things that could go wrong? Well, some of the things we were mentioning, right? It could have a gap. Or there could be sort of a break at A. Right? So something like that. Or something like this. Right? This is at A. Or you could have something like there's an asymptote at A. Right? Or like any situation that you can come up with, right? There could be like a vertical jump at A. This is what that way. Right? Notice that anything you can come up with that violates your intuitive notion of continuity will also violate that equation, right? Like how's the equation violated here?
It has a gap.
The limit exists, but the function is not defined at the point, right? So the right side of the equation doesn't work. What about here? Limit doesn't exist at A, because there's no right-hand limit. There's a gap here. It can't approach from the right. What about this? It's defined at the point, but it doesn't approach from the right. The limit doesn't work. So the left side of the equation fails both here and here. The left side of the equation also fails both here and here, because from the left you get a different value than from the right, right? The function is not defined here, so the right side of the equation fails here. Pretty much any case that you can think of where continuity breaks down, that equation won't work. And any case where continuity works, that equation will as well. Like all these notions, the complete intuitive definition of continuity is captured in this one little equation, just by knowing about the concept of a limit. Right? So there's a lot of information packed into this little thing. Like it's the star of calculus, the Higgs boson, the thing that holds everything together. Right? So you can get away with a lot of the limit. It's going to be how we develop the derivative, which we're going to do in chapter 2. How we develop the integral, which you're going to do in calculus 2. Right? But just know is that you can hold a lot of information in what we write here. And with that, we'll end. We'll pick up tomorrow with a quiz that comes up to that. Do I have all the homework?